Okay. Yeah, thanks very much to Marie and Matt for having me, and Holger for being on the local organizing, and all of y'all for being here. So I'm excited to give this talk. I'll preface it with I got in yesterday from the States, so of course if I say anything ridiculous, I'm going to blame it on my jet lag, since it is it's 2 a.m. for me. So I will do my best. So I've been at Vanderbilt since 2016. And a lot of what I'm going to talk about, we'll hear more about shortly, but we've been involved in a DARPA program called Assured Autonomy. And the whole premise of that, I'll talk a little bit more about, but that's kind of the background of this work. So it's a large DARPA program, and the idea is how do we provide assurance, and there's assurance case work in that. I'll primarily talk about our part of it, which is the formal side. So that's one method for generating evidence for some of those assurance cases. Yeah, so let's kind of get going. So of course, this is, I get to be up here speaking, but this is, of course, not all my work. It's mostly the work of our group. A lot of the work I'll talk about is by Tran, who's now at Nebraska, and Wei Ming, who's at Augusta, which is in Georgia, and quite a few other folks. I'm going to start off with some of Patrick's work, who's over at Google now. And then I'll also mention that Preston is here in the back. You can wave maybe. So, and Bernie is coming. I don't see Bernie here though, so I'm not exactly sure when Bernie gets here. But Bernie, both of them are here, and they have papers at SCFM. So, so that's kind of going on. Let me try to get started. Hopefully, videos are going to play okay and everything. So our motivation is autonomous cyber physical systems. Hopefully for this audience, I probably don't need to introduce that too much, but these are modern embedded control systems, specifically where we have a tight coupling between software and cyber processes and physical processes. So these are a couple cars, these small F-110 cars kind of running around our lab. And in this, I'm not going to actually talk too much about what I'm showing in the video here, but we're doing some online verification within these. So I'm going to start off with this kind of as motivation, but we're computing reachable sets online for models of these vehicles and seeing if they're colliding with each other with obstacles in this environment. Let me kind of keep going. So some other motivation. So we work in a lot of different domains. So Preston, who's here again, did some work with Air Force Research Lab, or AFRL, developing some safe reinforcement learning benchmarks. So this particular one in spacecraft docking. The AFRL has a team led by Carrion Hobbs, and a variety of other folks are involved. Nate's alum from my group as well, and is at AFRL now. But these are online. You can check these out. These are interesting sort of case studies that for verification purposes. So the goal of this essentially is to get these spacecraft to dock, and there's some assumptions, and obviously it's models. I'm not going to talk too much about these. I'm going to go quickly. This is all sort of motivational, and these are just some traces or time series data essentially generated from these. So this is going to come up maybe a little bit in the talk. I have too many slides, as one often does. So I may eliminate one part of my talk depending on how things go. There's another case study we've looked at, or that Preston helped develop, again with Dr. Hobbs at AFRL, in doing aircraft rejoin maneuvers. So if we have two aircraft and want them to kind of sort of group up together, and using, in this case, Dubbin's models of the dynamics of the aircraft. So again, not going to get into the details of this, but just motivational. Okay, so a variety of kind of case studies we've looked at. So in our DARPA Assured Autonomy project, we have been paired with Northrop Grumman, who's one of the platform and vehicle providers for this program. And so these are some of the autonomous underwater vehicles that are shown sort of here on the right. So this is Ivor from L3 Harris. That's an autonomous underwater vehicle. And I'm going to talk a little bit about this and sort of use this as one of the case studies for this presentation. So within Assured Autonomy, again, the goal is to create technology for continual assurance of cyber physical systems that have learning-enabled components in them. So we'll see that term show up, as well as this learning-enabled CPS. So most of the learning sort of in practice that's happened within this program was sort of a priori learning. So learning we do in simulation and then try to transfer to hardware, do some offline training and things like that. But you can sort of envision, in the future, maybe online learning and things actually sort of learning as they are deployed. And our role in this really is developing verification methods, and primarily formal verification methods, and working with Northrop to apply them. So one challenge problem that I'll sort of use to frame this presentation is in doing robustness verification for neural networks that are used for semantic segmentation. So if you're not familiar with semantic segmentation, I'll introduce it a little bit. So we're in like a formal methods venue, and I'm going to talk a little bit about some computer vision problems. But semantic segmentation essentially is you have an input image. It's going to get propagated through a neural network. And then what we're trying to do is classify every pixel into a set of classes. So in this case, we're identifying a pipe or something that we're going to track with this vehicle, right? So this would be the input image. This middle part is sort of a dead band. So this vehicle has side scan sonars. So that's just, the pipe is sort of this thing off on the right. And so we want to know where the pipe is so that we can follow it with the vehicle. So you can think of sonar. I don't know anything about sonar. Okay, that's why we work with platform providers and domain experts. But you can basically think of these as images after they're acquired. So we get one of these, it's basically an image, just like you'd think, kind of looks like this, and it would get processed. So you've probably seen this in other spaces. This is used a lot in autonomous vehicles, other forms of vehicles as well. So this would be the type of component that would classify, if I have like a picture of a vehicle, or like say you have an autonomous vehicle, like a motor vehicle, and this would, semantic segmentation is one of the things you probably use to classify like what's a pedestrian in pictures that are being used, where's the road, where are the road markings, all that. So this is a little bit simpler case. The particular architecture that I'll talk about for this, and I'll get into this, I've got to introduce a whole bunch of things to get there. This is a SegNet type architecture. So there's a sort of, it's an encoder decoder type architecture. So you kind of do a downsampling to this kind of feature space, and then there's an upsampling back to get to these, this kind of space of classes. Okay. So, so I'm going to briefly mention a couple things before I get into that and show you a couple scenarios of simulations with these, with the AUV. And I'm not going to talk much about our online verification work. I think this and the next video or two are pretty much the primary parts of it. I'm going to primarily talk about our design time or offline verification approaches, where we've made a lot of progress in trying to scale automated verification methods over the last few years. But I want to talk a little bit about this because in the overall process, the current kind of best practice, we don't fully know what to do for these type of systems that are going to have neural networks in them. And monitoring and actually monitoring what things are doing online is going to be an important component of this. So we want to do all this design time verification that I'm going to focus on, but then we're still going to have to monitor things online. This is the current best practice. And the key idea behind this work, and I've got a variety of references here to just sort of point you at them, is to abstract whatever the learning-enabled components or the neural networks and observe the influence of their behavior on a planter system model at runtime. So basically sort of propagate forward where a system would be into the future and do that in a sound way such that we're actually over approximating a set of reachable states. So I'll talk a little bit, just briefly a little bit more about that. Okay, so what does that look like for our UUV scenario, since that's what I'm kind of trying to use to motivate this? So hopefully you can kind of see the video. So this is where the vehicle started. There's a variety of obstacles. This is a simulation in a framework called UUV Sim. And what we're propagating forward here, these are reachable sets that we're propagating forward in time of the vehicle. And then it's trying to follow this pipe, which is blue here, while avoiding these obstacles. All right, and we have limited sensory range. There's, in addition to these side scan sonars that are used to sort of identify where this pipeline is, there's also forward-looking sonars that identify if there may be something in front of the vehicle to avoid it. So another one of the challenge problems that we sort of looked at with this, and again, Patrick led a lot of this work, would be in geofencing. So this is kind of one of the motivational scenarios that Northrop created for us. And this would be to be able to provide some guarantees that the UUV remains within a particular geographic region. There's many, many, many challenges here, and we're making lots of assumptions, right, about reliability of the perception in some cases, what environmental modeling we're doing. So in this particular scenario, we were considering some of the environmental uncertainty. So however, we're estimating the vehicle's position using there's essentially some fancy accelerometers and things within the vehicle. You don't have GPS because it's underwater. So there's a variety of kind of interesting environmental challenges. But this was one of the scenarios. And again, we're propagating reach sets forward in time for this, and sort of seeing the color coding was if this is the reach set of the vehicle sort of here going this direction, and it had earlier been colliding with whatever this obstacle would be. Okay. So hopefully that's some reasonable motivation of some of the type of systems that we've been looking at. So you can see it's from ground vehicles to air vehicles to space things to underwater vehicles. So it's been kind of an exciting place to look at things. So I'm going to try to motivate briefly since I don't, I mean, I didn't know anything about machine learning stuff until we started doing this a couple years ago. So it's, I think, a reasonable idea to try to introduce a few things. So I'll motivate, like, why should we even consider formal methods in this space? I'll talk primarily about approaches we have implemented in a tool called NNV. I'll give some pointers to some other things. Depending on how I am with time, I may jump over. I have a section on hyperproperties that we're using to try to formalize robustness of things like computer vision tasks. That's kind of ongoing work, and in a new project, I may skip a bit of that, but I'll try to get back to some of this classification and segmentation robustness. So for that AUV problem, this is a defense scenario. You could imagine a variety of things that could happen, and which I'll try to motivate in just a minute. If you're not aware, there are things called adversarial perturbations, which can cause a lot of issues when you're trying to use machine learning components, and that also applies to things like segmentation. Segmentation, you're solving a classification problem, but something even more complicated. I'll mention a little on some of our closed-loop verification, but I'm not going to focus on that, just kind of in the interest of time, because there'd be too much. Okay, take a sip of water. So we are putting machine learning components like neural networks into CPS. And these are, of course, those safety critical systems. We don't necessarily know what neural nets are doing. Neural nets also have a variety of risks that I'll show you if you happen to have not seen them. So broadly, we're calling these things LECs, just definitional. And these are being used kind of across the stack from sensing and estimation and perception through planning and control. So I'm not going to talk too much about control. I'm going to primarily focus on some of the perception things. So there are strict regulatory requirements in many domains for these systems that many of us in the room are probably familiar with in some domains, whether it's aerospace or automotive, medical devices, other domains. Some of these standards advocate, of course, usage of formal methods and verification in the development process for these systems. And as we're starting to put these data-driven components in it, we have traditional guidance for software components, but now this is like a whole new class of things we're trying to do. And again, we don't really fully know what to do for these things yet. That's my conclusion after having worked on this for 5 years. So much more research is needed. I'm going to give you some pointers to emerging programs. I'm aware of some European and UK programs as well. So a lot more research is really needed in this space. But this again is based on our interaction with a variety of industry folks in this space, particularly Northrop, but Boeing is also involved in the shared autonomy program, so is Collins, and then some other users of some of our tools or other automotive companies. So significant concerns, and again, the best practice really, the conclusion of this talk essentially before I even tell you too much more details is sort of analyze as much as possible a priori and then monitor everything at runtime. And I would even argue we should not eliminate humans from the loop, right? That's sort of, I think that's the best practice. So when I was in grad school, we were talking, how we were going to have autonomous cars, I think 5 years ago, and I think we've increasingly come to the conclusion that progress was being made, but there's still many challenges. So with that, some of you may have seen this particular image. So one of the big challenges when you have things like neural networks in these type of systems is that they're susceptible to what are called adversarial perturbations. So they're not robust to small changes in inputs. This can cause large changes in outputs. I'm not going to be too specific on kind of the terminological stuff. So, sometimes people call this a form of continuity, but broadly we're just calling this robustness. So this is an example from this I called CVPR paper, in 2018, which has had a lot of traction. There's many different types of these kind of things. Some of them, if you've seen this Panda and Gibbon thing, was kind of one of the first in this space. This is sort of a more real world instance with what would be a physical adversarial perturbation. So this kind of graffiti has been applied to the stop sign, and that's been designed in such a way so that the stop sign, by certain classifiers at least, is classified as a speed limit sign. So obviously, if you're using a camera on a vehicle, it is going to now have classified this as a speed limit sign. So what is it going to do when it gets there? Well, it's just going to go straight through the stop sign, right? So that's not good. So it's a huge safety risk. Many challenges. There's other forms of perturbations. There's a whole field of adversarial machine learning. We won't even attempt to review this, but there's even single pixel attacks. So we can sort of see this perceptibly, but there are also imperceptible attacks, right? That you won't even sort of see this. There's some debate in the community about whether these things can really happen in the real world or not, but I think the prior one hopefully sort of illustrates that. You can make arguments if you have video and so on. So these are a couple other pointers of some of the challenges of trying when we have these things, particularly for perception. So this is an interesting example of a 3D printed turtle. So it was classified properly as a turtle before a perturbation was applied to the turtle, and now it's classified as a rifle. So there's many different ways these kind of things can get selected, these perturbations and this noise pattern that you can generate. But we can't sort of see any difference in this turtle, right, if we're looking at it ourselves. And that you can sort of select the class essentially that you want to fool the neural network into identifying something else. Okay, so there's a lot of these instances. I'm not gonna sort of go through them. There's many other assumptions, like you have access to the model, you have access to the data set. Again, it's a whole field of what information you'd have available to generate those attacks. So they're advocates of why we should consider formal verification in this space. One is through this Assured Autonomy program. So this has been running since 2017, 2018. There's other organizations, of course. There's an EASA report that talks about some of these things and cites some of the work in the domain, including some of ours. Another conclusion is we actually need to say what these things should do. So how should we specify what these machine learning components do? So I think there's kind of really a grand challenge in formal specification in this space, and also assurance case work. I'm not talking about all of our work here. We also have like GSN work, full structure notation work, and actual further assurance case stuff in our broader project, but other people lead those. So analyzing these things, again, there's many challenges. And I would also argue, just in terms of sort of techniques, we need automated techniques here. These models are large. We also don't necessarily understand them. So I think we need model checking like approaches and probably not theorem proving type approaches. We could debate this, though. There could be some space for some theorem proving approaches for sure, especially if we're able to significantly automate things. Okay, so let me start to get into a little bit of the meat. So I'll talk some about our neural network verification software tool. So this was developed a lot by many people in our group, but particularly by Tran in his dissertation. We have a series of papers on this, kind of starting out from some theoretical things through different model classes, through different problem classes. So we started out with developing some of the data structures that are used in this. So how do we do this in the first place? Then some of the contributions we've made are in essentially data structures for representing high dimensional polyhedra, right? So that's sort of essentially some of the core technical stuff, and I'll talk a little bit about that. Let's see what else I mentioned. Right, we have a paper on if you're interested in the details of the semantic segmentation, which I'm going to mention some of, there's a CAV paper from last year on this. And then some more recent work that we have, we've also, in addition to just analyzing neural networks, I'll sort of tell you what this means, but this is kind of a typical verification problem. So we have some model, we also have some specification, and we want to analyze that. We use reachability-based approaches, and then we want to check if that model satisfies that specification or not. So it's kind of the classic verification setup you'd have, where you have a model of a system and a specification, and we want to prove that that model satisfies that spec. So the types of specifications for things like the image classifiers, we would have robustness as our specification. I'll give you some formal definition of that. And our model then would be, say, a feed-forward neural network or a convolutional neural network or the semantic segmentation neural network. We also have methods for doing closed loop analysis. And again, I'm not going to focus too much on this just in the interest of time because I'd have to talk all about hybrid system reachability and all sorts of things and probably too much detail that's kind of a more established field that's been around since the 90s. But in that, we'd have a plant model with a neural network that's controlling that plant model. So there's methods for these. Okay, so one question we often get, and just to sort of preempt it, so NNV is written in MATLAB, so we sometimes get some pushback for that, and I'll just sort of mention why did we do that. I won't focus on this too much. There's a variety of interchange, so we support ONNX, which is a kind of open format for representing neural networks, and this is integrated in with some of the other standard machine learning approaches. So one of the reasons we did it, one was we just made some choice at the time, but then also it did actually turn out to be a good choice for us at the time, in that many people in CPS have ended up started using NNV because it is written in MATLAB, and this fits in with their typical development process, because we often rely on things like Simulink for doing code generation. This is at least in the US. In other places, there are some other ways to do things. But for example, Collins picked up NNV because of this, all right? And it kind of fit in their typical development methodology. And there's many, many reasons for this, but we sometimes get this question, so I like to sort of preempt it. Okay, so let me tell you some about what we do and how some of this works if you haven't seen some of this. So we do reachability-based neural network verification. We're calling it reachability. There's other work in this space. You can view this essentially. So I come a little bit more from kind of a model checking world, but you can view this through the lens of abstract interpretation if you want. And there's work in that kind of space as well. There's other approaches for this, and many of the effective approaches formulate these problems as like mixed integer linear programming problems under a variety of assumptions of what the model type is. And some formulate satisfiability type problems as well. Okay, so what do we have though? So we have a neural network. I'm just going to call it M. I'm probably not going to be too consistent with my notation. But what is that? So this is, let's just suppose this is a feed-forward or convolutional neural network. So this is a mapping from some space to some other space. That's essentially all that it is. It's a function. So if we have a set of inputs from the input space, we're going to propagate them through this, okay? And we're going to get some set in the output space. So this essentially, this output reachable set essentially is the image or the range of that function under a set of inputs. That's essentially what we need to compute, right? So we're computing the image of this function under this set of inputs, and that's the basic idea. So now the problem is that this function is really complicated, right? This is a big function. There's assumptions going in here, obviously, right? I'm saying these are reals. Normally, we're running a neural network on a computer. It's actually floats and so on and so forth. There's some work in that, but this is just kind of the high-level abstract formulation. So then what we would do is we'd suppose our specification essentially then is defined in terms of what that set of inputs are, and then some region in the output space. And then we do kind of the typical thing you'd think of. We're going to check intersections and see if the output space intersects with a set in the output space. Then computationally, sort of what happens, we internally are representing things as convex sets, some form of polytopes or polyhedra. We propagate those through, doing a layer by layer propagation of polytopes, and then we may get a union of polytopes in the output space. And then again, what we're going to check is the image or range of this neural network function under that set of inputs. Is the intersection of that with our specification empty or not? So kind of a classic reachability formulation we'd think of if we were model checking, say, a safety property for a finite state automaton or something. Okay, so in a little bit more detail, and to just show you what this could look like for an example, this is an illustrative example for a very toy neural network. This is a randomly generated neural network, but it's just for the purpose of illustration. So this, again, in this formulation, we have our neural network M, so it's a mapping from R to the N to R to the M, and we have a set of inputs, and we need to compute this set of outputs. So for this example, our input set is some kind of like cube-looking thing, okay? So under whatever inf norm this would be, we're going to propagate this thing through, and we're going to get a set of outputs. And then we'll have defined our specification in the output space. So for example, say our specification is this rectangle in the output space. What we're going to do is from this cube, we're going to propagate that through the network and then see what that looks like in the output space. And what that looks like for this particular neural network, which is a mapping from R to the 3 to R to the 2, this particular network has 7 hidden layers with 7 neurons each using ReLU activations, rectified linear unit activations. I'll tell you what this is. This is a piecewise activation, but I have a picture of it in a minute. And this is what the output reachable set for this neural network would be under that set of inputs. So it's the union of all of these polyhedra, right? So that's the output set. So that's what it looks like for this particular example. So then we would check, does this set that we've computed, the union of all of these shapes, does that intersect with this rectangle or not? What we're also showing on the right side is just evaluations of that neural network, right? So just points. So we picked points in the input space, and then we're just running those points through. So sort of just as a sanity check. So if this is sound, we would expect if I took any point in this cube and propagated it through, that I should get a point in this that's contained in this union of all these polytopes in the output space, and that's what we see. So this is sort of the sanity check for soundness. Okay, so I'll tell you a little bit more about that. So let me stop. I see some, I don't know, dazed looks, I guess, or questions. Okay, no questions. All right. Again, I'm very jet lagged, so if I've said anything totally bonkers, let me know. Okay. Okay, so what are ReLUs? If you haven't seen these before, this is just a piecewise linear activation function. This is what it looks like. It basically will zero out things if the input to it's negative, and then it'll just keep it if it's not negative. I won't give like a full background of neural networks just in the interest of time, and also I don't want to insult anyone because you may know something about these. So there's a variety of challenges here. But if all of the activation functions in our neural network are ReLUs, this is a very commonly used activation function for a variety of reasons. But if they're all ReLUs, in the CAV ReLUplex paper from 2017, there's a theorem in it basically trying to solve this problem. They have a SAT formulation, but it's true for reachability too. Basically what can happen, and just to go back to my prior slide, you can see I had one set as input, right? But what happened, I have 1,250 polytopes on the output. So I can get an exponential blow up essentially in the number of ReLUs, right? So I have splitting. And there's a lot of the technical work in this space right now focuses on like, how do we reduce that splitting? How can we merge sets? How can we sort of abstract things and do things reasonably? But basically this is NP complete, and we may get exponentially many polytopes as we propagate through, so exponential in the number of ReLUs. Okay, so keeping track of that is a little bit challenging. So just to give you an example of what this looks like for a more realistic data set, so if you're not familiar, MNIST is one of the most common machine learning sort of image classification benchmarks, and the problem is to classify handwritten digits. So for this, an MNIST classifier would be a function that maps from images to classes. So in this case, these are 28 by 28 pixels. They're normalized into like 0 to 1 color values. And in reality, there's, I think, 8-bit color. So it's just grayscale. There's other variants of it where it's just black and white. But it basically be given one image, right? So given this picture of a 1, classify it as a 1, right? And we're all probably pretty familiar with this. Now, before I actually get to the space of classes, how does this formulation that I've kind of made look like? Before we would actually do the classification, if you're not familiar with how these work, our output space would be R to the 10. And then what's done in the final layer of a neural network, typically you take a softmax or an argmax, and you're essentially the class that you'd specify would be whichever one was the maximal. All right, so what does this sort of look like? This is the output reachable set. It's projected a bit onto the dimensions of the classes because this is a 10-dimensional space, so we can't really visualize what it would look like. But this is what this would look like. So for this particular image, I think it should be a picture of a 0. So say I'd put in a 0, and we'll have defined a set about that. I'll talk a little bit more about that in a minute. That would get classified as a 0 because this 0th dimension is the largest. So we take the argmax, and that would be the 0th dimension. So we'd say that this picture was a 0 because the 0th dimension was larger. Okay, now when we're doing this reachability formulation, you can imagine I have one of these images and I will have considered a set of images around it, right? So continuous set. So basically bloat that input image into a set of images, an infinite set of images represented as a polyhedron. And then what would that look like in the output space? Well, again, this is projected down because this is n r to the 10, so we're just sort of showing it for each of the 10 dimensions. But if the minimum, you can see these are all ranges now. If the minimum of the class we are interested in is greater than the maximum of all the other classes, then we'd say we've robustly classified it. I'm going to give you a little bit more of a math definition of this in a minute. So there's different data structures essentially that have been used for this. So one we developed is called image stars, which is an extension of star sets that I'm going to talk a little bit more about in a minute. But there's other data structures you can use in this space for representing the polyhedra like sonotopes and other forms. Okay, just to give you a pointer of, so I've talked, and I'm going to continue talking mostly again about the neural nets. But if our neural network was a controller, again, we also have some support for this in NV. For doing this, I would have a plant model and then a neural network model that's typically just a controller. This would be less so in perception. Perception, honestly, nobody has any idea what to do yet. But in if I have a controller for this plant that is a neural network, this would be what we classically called intelligent control systems in control theory. We can also do this, and what we do on the plant model side, we would consider differential equation models of this or hybrid automata models of this, and we've got NNV hooked up with some of the methods for doing hybrid systems reachability. Particularly, we use Cora from TU Munich, from Matthias Althoff's group. For part of it, we have some internal methods in NNV as well, but that's how we do that. And then if we are operating this periodically, which would be kind of a typical way these things would operate, so we periodically generate control inputs for our plant. We essentially do a form of bounded model checking, where I'd combine what I just have been talking about and about to talk more about with our neural network reachability. We'd combine that and use that as a set of inputs for the plant. So instead of just having one input for the control, we'd have a set of inputs. Okay, and there's a variety of challenges here. I'm not gonna get too much into this, but you can imagine it's sort of like bounded model checking. We'd unroll things up to some number of control periods. Right, and how would that work? Let me just give you a couple definitions of safety in that case, and then I'm going to kind of switch back. So we'd say the system would be safe in that case if the intersection of the overapproximation of the reachable states with unsafe states is empty. You can also think of this in our neural network case. So what would this tell us? If I have some initial set of states, I propagate things forward in time. You can also imagine this without time in our neural network case, but this would basically tell us there's no trace that takes us to the unsafe state. And then normally, for various reasons, we need to over-approximate things in some way. Except for some neural networks, if we have CAN-H is a common activation function that's used as well. This problem we can't solve exactly. We'd have to over-approximate things. And then for differential equation things as well, it's undecidable to actually do this computation, so you normally have to over-approximate things. Okay. So I think I've been going about 30 minutes. I think in the interest of time, I'm not going to talk about the hyperproperty stuff. This is the thing I was maybe going to skip over. If you're interested, I will come back to this, but I want to leave some time for questions and everything. All I'll mention is how do we specify things like robustness against adversarial perturbations. So it turns out that is a hyperproperty, which I haven't given you like a full definition to, but basically we would say a neural network is locally robust about some particular input point up to some value epsilon if for every nearby point we get the same class, right? So this would be for like a classification problem. So what does this sort of look like just intuitively? So we'd say I have an input. This could be an image, an imness. I'm going to perturb that up to epsilon in the space of images. If all of the nearby images get classified as the same class, then we'd say this is robust. What this is sort of telling us is that we aren't kind of running over the decision boundary to where we would change the class. If you go back to the stop sign example, what happened there essentially was we perturbed that image with some noise, some extra thing on it, in that case, the graffiti. And what happened was we changed the class, right? So in our sort of space, we changed what the decision would be. And that's why it was not robust. So if that had not happened, and if we had methods to analyze that, like what we can do with things like NMV, then we'd be able to evaluate the robustness and sort of say, yes, this thing is robust, or is it not? If it's not robust, you can use some of these methods for actually finding adversarial perturbation. So so this sort of necessarily requires multiple evaluations of this neural network, and that's why this would be a hyperproperty if you have sort of seen these. So this is something we're exploring in an ongoing project. It's kind of very ongoing work. Okay, so let me come back, have a sip of water. Let me tell you a little bit about how we do some of the representation of these sets and things within NNV. So again, one of the contributions in this space that we made is data structures. Essentially, this isn't like a BDD exactly, but you can imagine, right? This is a data structure for representing sets of states symbolically. So that's what star sets are. So what this thing is it's a tuple, and it consists of a center. It consists of a set of basis vectors and a predicate, and then there's predicate variables too. So I'll just do this sort of in the intro by example to kind of make it hopefully give you the intuition of what this sort of looks like. So say I want to represent the square in R2 as a star set. So how would we do that? So the star set corresponding to this would be comprised of these components. So the center of this would just be the origin, right? So it's just the origin, so that's the center. The basis vectors are just the orthonormal basis vectors, right? It's just the axes, okay? In this case, our predicate is a linear predicate essentially. So that's we have some matrix representing this, and then this D is another constraint sort of just defined by, right, that we want to represent this square, okay? And then the star set for this would be represented in this way. So what this lets us do, this is sort of how we internally are representing these high-dimensional polyhedra. We have zonotope methods implemented too, and polytopes. Some people, we also have abstractions where we just use hyperrectangles or intervals, essentially, some other types of things. So that's kind of the intuition. So there's a few properties of this. So any bounded convex polyhedron can be represented as a star set. So that's a useful property. So that means we can represent these things in this way. Another very useful property in the context of neural networks, most of the transformations in a neural network are linear or affine mapping, right? When you add when you multiply the weight matrix by whatever the input is and add in the bias vector, that's an affine or linear mapping. So the affine mapping of a star is also a star, so it's closed under this. And it's also pretty easy to compute this, all right? So you can sort of pretty directly transform this. So this is one of the things that help us scale this up. Another property that we need, particularly in the context of checking intersections, this is the intersection of a star with a half space is also a star, and that's sort of what this would look like. Don't dwell on the details. I'll just point out that a lot of this is in this FN paper from 2019. So why are we doing this? So the star set is efficient in affine mapping and intersection with half spaces. It's pretty easy to do these computations, and it also turns out it scales pretty well. So where this stuff arose, so my core community is kind of the hybrid systems community. This arose in hybrid systems. So we use this as an earlier CAV, I think 2018 paper, parsimonious, I can find the reference if you want. I don't remember the exact, parsimonious reachability or something by Sridhar Dugarala and Mahesh Viswanathan. But we use this in some other domains as well. So we've considered very high-dimensional hybrid systems for verification purposes as well, where we use this, right? And that's kind of, we've sort of ported this technique that was being developed in hybrid systems into this space. So how do we use this again? So this is a data structure that's used to represent infinite sets of inputs for our output reachable set computation problem for neural networks. So basically, we're going to represent our polyhedras as this. It's a data structure. Just like if you're using BDDs or something to represent classical model checking symbolic sets of states, right? It's the same idea. Our model checking problem here is sort of simpler in that we don't have state. This is a feed-forward network. There's no internal state, but the computation, of course, has some state involved. So what this lets us do, this is not a testing approach, this is a verification approach. We are considering an infinite set of images simultaneously since we're working with a real abstraction, right? So we're sort of considering all those images. There's all sorts of details, of course, with with respect to floating point and all these things, which I'm happy to talk a little bit about. The classical approach you do here would be a testing approach, and it turns out, right, you can always, if we are actually considering reals, you can always beat things like Monte Carlo just by considering a huge number of inputs, right? So at some point we will actually beat that, even though this reachability computation is quite expensive, right? So if you're doing testing, first off, it's not going to be sound, but then second off, we will actually scale better than that because you need to try an infinite number of inputs, and you at some point will reach that threshold. Okay, so we have an extension of this in the CAB paper for a data structure called image stars, which is for handling things in CNN. All right, so what does this kind of look like? If we compare this to a few other data structures, so zonotopes and some other data structures have been developed. So this representation allows improvements in speed up versus some existing methods, at least at the time. This field, during this talk, the joke is, right, there's a new neural network verification paper that's already come out as I've been speaking, right? So this field moves very, very quickly. Since it's sort of in the intersection of machine learning, so it moves super quick. But this is true as of our like our FM paper at least. So we had some comparisons in the paper to ReLU-Plex and some of the tools out of ETH Zurich within Iran. So they have kind of a series of papers and different tool names for some of these. So I'm not harping sort of too much on it, but I'll mention that we can represent the output reachable set both exactly and over approximatively. So that's why I mentioned a little bit earlier, kind of there is a relationship to abstract interpretation. We can do abstractions as we're doing this, which is key if we're actually going to scale this. And one of the nice properties of the star set data structure is what's commonly kind of done in this space, this is for ReLU activation, we can consider both an exact and an over approximative representation. So the exact representation would be this kind of blue line. That would be the ReLUs under some interval input essentially. And then a common abstraction would be to consider sort of this triangle. Okay, and other data structures, right? If I was doing this with zonotopes, this is what it might look like. And there's of course some benefits of using things like zonotopes where it has some symmetry and there's some nice sort of properties that can happen for that. Okay. Just to show you what this would kind of look like, and also just to briefly introduce this example if you haven't seen this. So one of the common benchmarks in this space are these ACAS-XU neural networks. These were introduced in the ReLU-Plex CAV paper in 2017. So this is collision avoidance for small uncrewed aerial vehicles where there's a vehicle where we're generating controls and there's some intruder vehicle that may collide with it in an air collision avoidance system. Very fascinating example in the backstory of how this got created, but this is advisory control. It's actually a quite complicated example and benchmark. It's a little hard to describe, but just to give you kind of a little bit of the intuition. The inputs to this neural network are essentially all of these states. So estimates of headings and velocities and distances between these things. And the output is an advisory, which essentially is what should ownership do to avoid collision with the other. And for a variety of reasons, this actually is neural networks. If you can imagine, why would I ever do that for an aircraft collision avoidance system? But there are some design constraints for why that's being developed. Particularly some of the methods for how these were created. It's an abstraction of a very, very complicated lookup table essentially, which was created from, I don't remember if it was Markov decision processes, but some kind of Markovian model. Okay. Okay, so for ACAS-XU, what could some of these things look like the star set representation? So these different kind of colored shapes in the middle, the union of this would be the exact set of reachable states for one of the ACAS-XU networks. under some set of inputs. So there's a variety of specifications for this, and I'm not going to go through all the details in the little bit of time I have remaining. But we could compute that exactly. We can do that over approximatively using the star set. And then this is just sort of a comparison to some of the other data structures essentially that are used in this space, like zonotopes or abstract domains. All right, and the point of this was we could sort of, if this is smaller, then we have less over approximation error, which can be key. So that can, depending on what the sort of example would be, this could even get more extreme, right? So for zonotopes, the over approximation error may be very large, and that can be problematic because then you may be too imprecise to actually prove a property, right? So this particular work, again, this moves very, very fast. This is from a year or two ago, I guess, probably about 2 years ago. There are now CGAR type approaches that people are doing to do automated abstraction refinement and all sorts of things that we can point you at if you're interested. Okay, so one other example, I mean, MNIST is sort of a toy. It's a very useful toy. We've also considered, I'm getting back to my segmentation problem, I'm almost there. A portion of that segmentation network is VGG16. So this is now, VGG16, I think was developed in 2015. This is now like a horrifically outdated neural network architecture, but it was one of the very effective classification approaches for the ImageNet data set. So in ImageNet, you have 1,000 classes and of images, like a bell pepper, a lemon, there's all sorts of things in this. And the problem is to identify what the class is of that image, right? So it's very large. The networks for this are quite large. The weights to represent this network is like, several hundred megabytes, okay? So it's a very large network. 16, because I think there's 16 total layers and so forth, and different pieces of this. I'm skipping over lots of details, obviously. This particular network does have ReLUs. It has convolutional layers as well. We have to handle these things. It also has another form of layer called max pooling. Max pooling is a very difficult layer to sort of handle, but I'm going to kind of keep moving in the interest of time. So for this, getting back to our adversarial robustness problem, so if I have an input image that's, say, a bell pepper, say I perturb it with some noise, again, plus or minus a set value of noise, will I classify it correctly or not? And can I identify how much noise could be allowed? So sort of how robust is it? So with this level of noise, which is sort of pretty imperceptible applied to it, we classify the image still as a bell pepper, or VGG16 would, and with some more noise, we'd classify it as a lemon. All right, so this is sort of the problem. I can't see the difference here, and if you're on Zoom, probably definitely can't. I can't tell the difference between these pictures, right? They look like the same thing. So is it robust, and can we analyze that? So like the MNIST thing earlier, it's kind of the same setup. Instead of a 10-dimensional output, we now have a 1,000-dimensional output. This again is projected down, okay, because I can't envision a 1,000-dimensional shape. And this is just projected down onto those 1,000 dimensions. And if the min of the bell pepper class is greater than the class of all the others, and the closest one happens to be the lemon class, then we would say that this is robust with respect to this test input image up to this amount of noise. So essentially we've said all the nearby images, if they're slightly perturbed, from one image, okay, this is local, it's not global, from this one image would be classified properly. Okay, some more details on that in the CAP paper. So I'm almost, how much more time do I have? Like, okay, because we have questions and things. So we've done some analysis of this across data sets. So what do we do with this, right? So this is local in the sense that I am looking at test inputs. That is like totally unsatisfying from a formal methods perspective, right? We're going to prove things for like all inputs and things. For these kind of systems, we can't really do that. So what you do is in addition to doing an accuracy evaluation across a data set, like when you're training a neural network, right, you do a split into, there's different ways to do it, but a training data set, a testing data set, and so forth. And you see after creating the neural network on the testing data or on the training data set, you see how accurate it is on the testing data set. So you can do similar, we need to know what all the proper classes are and everything, but we can do similar things for robustness. So what you can do in addition to an accuracy measure is you'd come up with a robustness measure. So for how many input images, what percentage of them were you able to prove it robust? You get a robustness percentage in addition to an accuracy percentage. That'd be kind of the idea. Right. So think I'm almost done. I'll get back to the semantic segmentation thing. So again, our input image for that would be an image. It could be color, and our output would be an image where we've classified every pixel. So we'd extend our definition of robustness for classification to this case, and essentially we do the same type of thing for this. Let me just show you kind of what this would look like pictorially in the interest of time. So we've done some evaluation with different data sets. There's a multi-digit version of MNIST called M2NIST, where I have multiple digits in the input. Instead of just a single digit, I have, like there's 2 ones in this image. And it uses the background as some other class. How this would look, in the output space, I would classify every pixel, right? So I'd say there's background, that's this red class 10. Then these kind of blue digits, that's what's gotten identified as the digit 1. And then none of these things are going to be perfectly accurate. You can see there are some pixels that are classified as other classes. Like I think some of the pixels are 7 and 6 and so on, okay? So even for the most state-of-the-art network. So we can do adversarial attacks for these things as well. And we'd answer questions like how many pixels are robust and sort of extend those definitions. That'd be kind of the idea. And we've done some evaluation of this on MNIST, M2NIST, or on M2NIST as well as MNIST, where we just use the background as where the digits are as the segmentation mask. Okay, so, and yeah, I think I'll kind of move on. Okay, let me. I'm almost done. I think timer's almost up. So for our Northrop Grumman underwater vehicle problem, what did we do? Well, we analyzed the robustness of the neural network used for doing segmentation here, and we're able to evaluate this on their network. And so we could prove absence of adversarial perturbations of a certain size across the test data set. So I do have to be a little bit vague here, but that's the basic idea. All right, so we applied it back to this and could establish some robustness properties for the data sets that we have for these things. All right, so I'm wrapping up. So what can we use in NV4? We'll prove specs hold for neural networks in terms of these input-output specifications. We can characterize robustness, local adversarial robustness, and so on. We can generate counterexamples too, and we can also prove properties in closed-loop systems. So this is kind of overall trying to provide assurance. So I mentioned some other things. If you're interested, we're sort of active in organizing things like the verification of neural networks competition, VNN comp, so similar to their formal methods competitions. This has been running the past few years. We have a really cool benchmark from Collins that they submitted this year, where they're using a convolutional neural network for prognostic problems using remaining useful life. The details of that are here. And I'll just give a couple pointers to some of our other work just real quick. So we have another tool called VeriTech that Xiaodong developed with Toyota. There's a paper 2 weeks ago at formats on this. We're also doing neural network repair. There's some other data structures within this. We can do some cool counterexample generation, which is, I don't know, the bottom left is kind of finding what region of the input domain is safe and unsafe for things like HSCC. And I'll mention Preston's work. So Preston and Nate. So Preston's going to give the talk at SEFM on some signal temporal logic work. So come to Preston's talk. That'll focus more on the closed loop type of things. It's a little bit less verification, but it's about creating controllers that satisfy SDL specs. And Bernie, who I think I saw come in, somewhere in the back now, come to Bernie's talk too at SEFM. Bernie's been working on behavior tree verification, and we have a tool called BehaveVerify for doing that, where we under the hood use NewXMB. So if you're interested in that, this really big, we've also done planning stuff in the Northrop problem, and we're using behavior trees for doing planning. So we've verified this particular behavior tree, which is used for that underwater vehicle. So I'm kind of wrapping up. There's a lot of other cool work, and I'll try to leave some time for questions. These are just pointers to other events. I can pull these back up. I'll just mention there's like significant interest, of course, in the space. not only assured autonomy, there's a follow-on program to this called ANSWER, which is getting kicked off with neurosymbolic approaches and lots of other cool things. So being in comp and so on. We just to give a little bit of pointer at that, NSF in the U.S. at least is very interested in this space as well. And last week we had a very cool workshop where we had the director of DARPA's Information Innovation Office give a phenomenal talk on sort of the need for formal methods-based approaches in AI. And then Deb Raji also gave a phenomenal talk on broader things. So we're talking about autonomy here, but this is affecting everything. Admissions decisions with neural nets, job hiring, medical imaging stuff, all sorts of things. Okay, so being in comp. So I'll conclude with kind of the medical imaging. We have a new project where we're doing this in medical imaging analysis in conjunction with Vanderbilt Medical Center. So we have a phenomenal computer or a medical imaging analysis group. So we're working with physicians and people who are really experts like EPEC on doing segmentation of medical images. So this commonly shows up in that where you may segment and find, say, a tumor. All right, so let me thank y'all and thank the group again. Again, Preston, Bernie here, come to their talks, please. And then I will kind of conclude that we have open positions. If you are interested in these things, feel free to reach out. Okay, thank you so much.
Great, thank you.